Hello everyone. In this lecture, we'll be looking at multi-level page table and then inverted page table, and we'll see how we can cache these page tables in a structure called in like hardware component called translation look-aside buffer. So reading assignments for this part are Dinosaur chapter 8 and chapter 16, 17, and 18 from comment book. So what we have seen in the earlier lecture or like last lecture is we have seen there are the statically operating system can manage memory that belongs to various processes by using simple multi-programming model where each process contains one segment, and then the segment can be located at any place. However, it has various drawbacks. Then we saw how all these drawbacks can be solved by using pages, where the memory, both physical memory and the virtual memory of every process, is now divided into parts called pages. So each page is of same size in across all the processes, right? And we also saw how we can store this page table. So specifically, we looked at memory management unit, which is a simple hardware component, basically the translation hardware, which assists us in doing the conversion from virtual address to physical address. So we saw that in memory management unit, we just store the base address of the page table. Okay, so uh, the page table, like whenever operating system does context switch, operating system changes the page table base address in the memory management unit to different address that actually holds the page table belonging to that current process. Okay. So this actually adds a restriction, because now we want to make sure that page tables are all contiguous in the physical memory, right? Because whenever a process needs to access some address, it gets is the base page table base address from MMU. So in order to access any memory, the page table has to be contiguous, right? So but this restriction is actually too large of a restriction, because page table size could be large. Like for instance, on 32-bit machines, you could have the entire page table of a process could be of 4 MB. And this could be potentially large on, for instance, 64-bit machines. Okay. And finding consecutive memory, like finding 4 MB of consecutive memory in RAM could be hard, especially when there are multiple processes running. It could be hard. How can we how can we solve this? How can we be flexible? Basically, like how can we split this page table into multiple smaller components so that we can evade this requirement of having contiguous 4 megabytes of memory. So as with all these problems in computer science, we can solve this problem also with the level of indirection. Okay, so the way to think about it is, so okay, so what happens if we split the page tables into multiple parts? Okay, the thing is, now we need to have another structure which should tell us where these multiple parts are, right? So this is what we call indirection. Okay, we use the same principle. What we come up, it's two-level page table. So here, instead of using one page table for the entire process, we actually split page tables into multiple parts, and each part like into equal chunks, and each chunk, the address of each chunk is stored in another structure called page directory. Okay, now given a virtual address, we take the most significant bits as an index into the page directory, which actually contains the address of corresponding page table. Okay, and then we use that address to access the corresponding page table, and then the same thing as paging happens afterwards. So this is very nice, because now we can have smaller page tables. So specifically, let's say now, instead of having in case of 32-bit address space, we can have most significant 10 bits as an index into a page table directory. Okay. And then the page table directory actually holds the address of different page tables. Okay. So each entry is an address to a page table. And then the next 10 bits are actually indexed into the corresponding page table. And finally, the target page table holds the physical page address, and this we just get the offset from the least significant 12 bits, and that's how we access the memory. So here now, memory management unit just contains the base address of page directory. Okay, it doesn't contain the base address of all the page tables, but rather it just points to the base directory. So here CR3, we can consider CR3 as the page table base address registry, or like the page table base registry in MMU. So here, what does this buy us? So one thing, now we don't need to store the entire 4 megabyte of the page table structure into the memory, because now we divided the page table, the big page table, into like 1024 4 kilobyte chunks. Okay. And then we are maintaining another structure called page directory, which requires another 4 kilobytes, which is a page, which actually stores the pointers to all this 1024 page tables. Okay. Now we don't need to store 4 MB in a continuous manner, right? And all we need to store is 4 kilobytes in a contiguous manner. That anyways we can do it, because each page frame is anyways 4 kilobytes. So this is extremely good. This is the power of indirection, right? Like all we added is just additional 4 kilobytes. That's it, and we were able to solve the problem of storing the big page table in a contiguous manner. So multi-level page table, specifically like two-level page tables, also provide another advantage. So let's look at an example. So let's consider process A, which has 32-bit address space. And let's say process A has only 6 pages in total. So the first 2 pages start at address 100, and it has 2 pages starting at that address. And other 4 pages start at 0f00 to, and there are 4 pages starting at that address. Okay. Now, if we look at the two-level page table for this process, so for the first 2 pages, the corresponding entry in the directory, it corresponds to 0x000. So here, the, that entry is valid, which actually points to the page table. Okay. Similarly, for the other set of pages, 0x0f00, so that maps to 0x0f0, and that entry is valid. And none of the other entries in the page directory are populated because they're all invalid. Okay. And only 2 entries in the page directory are valid. So this enables operating system to be very flexible. Right now, operating system need not populate all the directory entries. All it needs to do is it can actually populate them on demand whenever process needs them. Right. And note that the total space needed here is actually for page table directory, which is 4 kilobytes for the entire page table directory. And we need 2 page tables, one for each valid entry. So in total, we need 4 kilobytes to store the page tables corresponding to the process A. Okay. Which is kind of proportional to the amount of memory that it is accessing. Okay. Compare this with the flat page tables. There we need 4 MB of memory to store all the page tables, which is insane, right? So here, this two-level page tables also provides this very nice advantage of storing page tables on demand and being efficient in creation and management of page tables. Okay, we only manage page tables which are needed, absolutely needed by the process. We don't maintain the entire page table, right? So this provides additional flexibility of being very efficient, like being very memory efficient. So we can extend the similar concept. We can use, instead of 2 levels, we can have multiple levels. Again, here the concept is same. So in case of 64-bit address space, we can actually split the page tables into like 4 levels. And then we use the same logic as 2-level page tables to split each page each page table, like each level page table into a, so that it can be stored in a page, and then so that we can assign, or rather manage each l- table at each level on demand. So now splitting it to multiple levels provides us flexibility, right? Now the number of page table, the number of metadata, for instance, here there are four levels. So the number of metadata that operating system needs to manage is proportional to the address space, or rather to the memory that is accessed by the process. So in other words, operating system doesn't do any additional work that is not required to manage the memory of a process. Okay. So yeah, multi-level page tables has the same kind of advantages as two-level page tables. Here, the page tables, the entire page table need not be contiguous, right? So now we have split the entire virtual address into small chunks, and these chunks need not be contiguous. But like each, although each page table, uh, so here each entry at every level, it needs to be contiguous, but multiple entries need not be contiguous, right? And they need not be allocated before use. So operating system can allocate each page table at each level only when it is needed by the process. Okay. So what happens is when the process runs, operating system can have only one page directory. Okay. So when process is actually trying to access the memory, that's when it can populate the corresponding entries in the page directory and all the other page tables in the chain. Okay. And furthermore, these can be swapped out to disk. So we'll look into this later in the next class, where we will discuss dynamic memory management. But uh, one thing to remember is that this allows operating system to store the page tables onto the disk when the memory pressure is high. Okay. Again, this is all because of extra level of indirection, right? All we do is just add another layer of indirection. So, and instead of two-level page tables, we can actually combine segmentation with paging. So here, as you can see, we can have segments for and where each segment could be managed by using pages. Okay. So this is actually used in earlier IBM systems. So here, the top, like the significant bits are indexed into a segment, and the segment can be of different sizes, and each segment entry in the segment table points to a page table that stores that stores the mapping between the virtual address of that segment to the corresponding physical address. So so this actually makes the memory of each segment manageable by the operating system, right? And segments could be logical units for the process. So process can make like its code region, code, data, and stack as segments, which are much more natural to the compiler, and uh, and these segments could be managed by using pages. Okay. And segments, this actually allows us very nice advantage that unlike page directory, like page table directory, where each entry in the directory is of fixed size, here segments can be of different sizes, right? And finally, this finally, using pages after segmentation enables operating system for ease of management. And so at the high level, you can consider that going from page tables to pages and segments is like going from single segment to multiple segments, only at higher level. So when we have in the earlier case, when we have page tables, consider that we have only single segment whose size is the entire address space. Okay. Whereas Using segmentation and page tables, it enables us to split the memory into various smaller chunks of different sizes, and each chunk is again maintained by page tables. And one thing to note here is, again, like this brings back to our very old principle of separating policy from mechanism. So if you think deeply, actually page table, like two-level page tables or like multi-level page tables, are similar to segmentation plus paging. So in principle, right, their mechanisms are similar. However, policy is different. That means the hardware that is needed to implement segmentation plus paging or multi-level paging is actually same, whereas the differences lies in how it is used by the operating system. That is the policy. So using segmentation and paging, we still have the notion of segments, and it also allows us to have different sizes for each segment, whereas multi-level paging just splits the entire address space into equal chunks of, basically chunks of same size, whereas segmentation, we can have chunks of different sizes. Okay. So Intel Pentium, like the ones that we use, even they actually support segmentation and paging. So here, each segment could again be managed through multi-level page tables. Okay. So here you can see that processor supports segments. Okay. And each segment is further managed by using multi-level page tables. Okay. So as we saw in the previous lecture, there is still a lot of metadata that needs to be stored by the operating system, especially to manage page tables. So in total, like irrespective of whether they are contiguous or not, how many page table entries we need for, like in case of 32-bit machines? Like in worst case, it's 4 MB for each process, and we need to multiply it by number of processes. Similarly, on 64-bit machine, we have the same issue. But one thing to think about is the physical memory is fixed, right? So it doesn't matter which process is running, we have the same physical memory. Why we need to store different page tables for each process when we know that the physical memory is fixed? So this is the idea of inverted page table. So here the idea is, instead of maintaining the map from virtual address to physical address, can we do the other way? Can we maintain the map from physical address to virtual address? So this actually intuitively kind of makes sense, right? Because the physical address never changes. So once, like, if there is 2 GB of physical RAM on my machine, all I need to maintain is the page tables that are needed for only 2 GB of my memory. That's it. So I don't need to care about how many processes are using that memory. No, I just need to maintain one set of page tables and I'll be okay with it, right? So that is the basic principle of inverted page tables. So here we have mapping from physical page to the corresponding virtual page, right? So whenever a physical page is assigned to a different process, we just assign that particular virtual address. We just update the inverted page table. So here the thing is, so we have one common inverted page table global across the entire system. So whenever some physical page gets assigned to a process, we just update the corresponding virtual address in the inverted page table. That's it. So now we don't need to maintain virtual page tables for a different process. All we need to do is we just have one page, one inverted page table, and we just update the virtual address in the inverted page table. So this actually intuitively makes sense, right? However, The problem becomes lookups, where let's say, as we know, when we have to convert virtual address to physical address, all we have access to is virtual address, right? So in case of inverted page table, what happens is, now given a virtual address, in worst case, I need to go through all the entries of the page table to identify the corresponding, like to identify the physical page corresponding to the virtual address, right? So there is no direct mapping as with the case of virtual address, as with the case of regular page tables. So here lookup becomes a problem, because now I need to go through the entire inverted page table to find the entry corresponding to a given virtual address. So to make this lookup more efficient, hashing is commonly used. So wha- here the thing is, we use a hash as an index into the inverted page table. So the hash is composed of process ID of the process and the corresponding virtual address of that process. So this is maintained in such a way that whenever when we compute the hash of the virtual address and the process ID, the hash is an index into the inverted page table. So when you index using the hash, that could that actually tells you the corresponding physical page. Okay. So this is good, but still, like, there is a problem of, when multiple processes when multiple processes have the same hash, we need to do hash chaining, so on and so forth. Like all the problems that happen in, like, hash collisions also happen here. So the lookup, or like the management, becomes really hard. And one amazing advantage of inverted page tables is very small page table, and one page table for all the processes. Okay. And context switch becomes very easy, right? Now operating system need not worry about memory management, what's like doing any uh, metadata management for memory at all. All it has is one global page table, and whenever context switch happens, it doesn't need to do anything with respect to memory. The problem becomes tricky uh, when multiple processes wants to share the same physical page, right? So in case of page tables, that was easy because we just have the same physical page in the corresponding page tables of two processes. Whereas in case of inverted page table, how can this be done? Because inverted page table has one entry for one physical page, right? However, uh, we want to have two processes access the same physical page. It becomes really hard. So, like, for this reason, most of the modern operating systems, they don't use inverted page table. They usually, like, it's the multi-level page table that's the common. Like, most of the systems, like almost all the systems that we use, they use multi-level page tables. Nobody uses inverted page tables, just because, like, the lookup is very hard, and sharing of physical page across multiple processes also is hard. Okay, in the next part, we'll look into TLB, one of the amazing hardware component that helps us in doing memory translation more efficiently. Thank you.